Peace and prosperity. Today we're going to talk about applied gunsmith measurements and torque principles. But before discussing operations, our primary safety work perimeter is verified code. My workbench contains 0 live ammunition, no primers, and no explosive components. To prepare for this briefing, I thoroughly analyzed my Gunsmith Module 3.1 through 3.4 regarding gunsmith mathematics, precision tooling, and torque parameters. Today I will demonstrate micro tolerances. While most gunsmiths' workbench utilizes calipers, my station is uniquely deploying an outside micrometer for maximum precision, though I will thoroughly break down caliper theory and application. Let's engage with caliper proficiency and high precision theory. While digital calipers are the universal staple tool for rapid measurements down to a half thou or 0.0005 inches via an LCD screen, they rely on a sliding jaw contact that can flex under hand pressure. To demonstrate proper, uncompromised measurement techniques today, I am deploying this outside micrometer. To capture a measurement correctly, I position the component squarely between the anvil and the spindle. My hand positioning grips the insulated frame to prevent overexpanding the steel tool. I rotate the thimble smoothly, utilizing only the ratchet stop at the back. This ensures perfectly uniform, repeatable pressure without crushing the component. I'll quickly demonstrate using this household fastener, which is really a screw. As you can see, our baseline reading measures precisely 0.111 inches. If we look at dial calipers, they display fine measurements down to 0.001 down to 0.099 on a physical dial mounted directly on the movable jaw. Some gunsmiths choose a dial caliper when working around high magnetic fields or harsh cleaning solvents that will immediately fry a digital LCD screen or drain its battery. However, a micrometer remains the absolute king when absolute accuracy is mandatory, such as verifying a firing pin protrusion to avoid ruptured primers, or measuring a custom cut barrel tenon where a mistake of a 1 thou indefinitely ruins head spacing jobs completely. Moving into fastener identification and thread analysis. Legit gunsmiths cannot guess thread configurations. Foreign manufactured firearms routinely mix metric and imperial fasteners, and using the wrong one will cause catastrophic thread stripping. I have gathered 3 distinct machine thread fasteners to analyze. Fastener 1 I have taken from my ARP scope, right here. I place the threads inside my micrometer to measure the major diameter, tracking at exactly 0.1045 inches. I now overlay my thread pitch gauge until they lock flush without daylight showing. It matches the 32 threads per inch leaf. This identifies as a standard number 1032 UNF screw. For fasteners 2 and 3, I gathered from the pistol grip of my TAC 14. Micrometering tracking puts this fastener directly at 0.206 inches. The pitch gauge leaves locked perfectly at 40 TPI. This confirms it is a standard number 6x40 firearm screw, a common thread profile used for mounting scope bases. For fastener 3, my micrometer reads flat at 4.00 millimeters. Swapping with my metric pitch gauge leads, it tightly meshes with the 0.221 millimeter leaf. This confirms it is a metric M4 by 0.7 fastener. The primary difficulty in this tracking exercise is avoiding canting the micrometer spindle against the screw crowns, which artificially screws the diameter reading down. The skill is critical when fabricating a missing vintage screw on a lathe, or selecting an exact tap to clean out a stripped receiver hole. Let's transition into torque specs and application. To properly set this torque screwdriver, I release the locking collar at the base. Rotate the handle until the internal dictator lines up precisely with my target value of 30 pounds per inch. When driving the fastener, I maintain vertical alignment and rotate smoothly until the internal clutch clicks. Mechanically, there is a massive mathematical boundary between inch pounds and foot pounds. Inch pounds measure low-level rotational force applied 1 inch from the center of the fastener. Ideal for delicate applications, foot-pounds handle high-leverage structural tasks. Because there are 12 inches in a foot, 12 is our mathematical constant. If a barrel nut requires 4 foot-pounds, we multiply 12 to set our tool to 48 inch-pounds. Understanding torque is non-negotiable across 3 critical gunsmithing applications. First, scope rings and bases require roughly 15 to 30 inch-pounds. Under-torquing causes optics to shift under recoil, while over-torquing courses the main tube and strips the receiver threads. Second, action screws hold the receiver to the stock metal, requiring 30 to 65 inch-pounds, depending on whether you are dealing with unpillared wood or rigid synthetic bedding. Improper torque can cause stock crushing or erratic barrel harmonics, which can lead to destroying your accuracy. Third, AR barrel nuts demand a wide window of 30 to 80 foot-pounds, solely to align the gas tube gas path. Exceeding 80 will instantly fracture the aluminum upper receiver threads entirely. In professional integration with the firearms trade, precision is our primary currency. A gunsmith's reputation and customer satisfaction depend entirely on the ability to work within precise manufacturing guidelines, rather than relying on unverified guesswork. When an unfamiliar weapon or custom component arrives at my bench, I don't assume anything. I deploy my micrometer, mapping dimensions, check head stamps, and research factory specifications before any of my tools ever touch any firearm components. By committing to exact measurements and rigid torque specifications, we ensure our custom builds are precise, our clients remain secure, and our workshop avoids catastrophic mechanical failures. Thank you all for watching this presentation. My workbench is now secure. Godspeed.